I'm Alex, and I am a research scientist at the Conversational AI team at Uber AI. And today I will talk to you about Plato, a framework that we released about 2 months ago for doing research and development on conversational AI agents, and also some exciting new research that we have done using Plato on training conversational agents in real time by having them talk to each other. So I'm sure you're all familiar with conversational agents. Virtually every big tech company has one, like Siri, Cortana, Alexa, Watson, and so on. And of course, many other traditional companies. And I don't know about you, but I'm losing track of how many startups there are out there coming out that are doing things related to speech and language. And of course, at Uber, as you may have guessed, we also work on conversational AI. And we have been rolling out some exciting new features. For example, on the, on the left of the screen, our smart reply system where when, for example, a rider sends a message that says, hey, I'm waiting near the Starbucks, we are predicting a set of plausible responses. So then the driver partner doesn't need to take their hands off the wheel, grab the phone, and type a message. They can just do one tap, select the response, and send the message to reply. We've taken that, we've taken a step beyond that and have enabled driver partners to use their voice to accept or reject a trip. So when a new trip arrives, the system will say, will ask them to accept or reject, and they can just say yes or no. They don't need, again, to take their hands off the wheel. This can be very useful in many applications, in many cases, I guess. And on the right-hand side, we have our voice reply system, where then you have, for example, a rider that sends a message that says, again, hey, I'm waiting by the Starbucks. And so the driver partner can reply using their voice. So they can say, hey, tell them I'll be late. So we can grab that intent, change it a little bit, and send the message that says, I'll be late, and send it to the rider. So again, they can be focused on the road and driving and don't need to do anything with their hands. But going back to conversational agents, as also Joe mentioned before, all of these agents that we are usually familiar with are assistants, but actually conversational agents don't need to be assistants. They can have different roles, for example, be tutors or coaches or health mentors or companions and many other things. And all of these applications, have different challenges that they bring. And more than that, the devices on which the applications are deployed have their own challenges, like is it a smartphone, is it a smart speaker, is it a robot, is it a car, all of these things create many challenges, and some of these, are not fully solved. For example, multi-party interactions. Imagine we have a lot of users, a lot of agents, maybe one agent, maybe a lot, but how do we keep track of the conversation? How do we know which user is talking, if they're talking to the agent, if they're talking to each other? How do we keep track of who said what and who do we speak to? Then multimodal agents, if you have, for example, robots, how can the agent take into account other signals, not only speech and text, but maybe other audio signals, other sensory input, cameras, multilingual agents. And by that, I don't only mean, train your statistical model on English, apply it on German, but how can we have an agent that can code switch between the languages in the same sentence? How can the agent understand humans doing the same and having kind of a nice flow in the conversation? Turn taking and bargings are always a problem. Emotion understanding, emotion expression, common sense reasoning, and of course, if we have embodiment, whether it is a 3D avatar or whether it is like a robot, there's a whole set of other challenges, and socially skilled agents is another chapter. So at Uber, we work on a smaller set of these challenges, but we are a young team, but we have been very productive. And these are some examples of the kinds of work that we have done. For example, concurrent training of conversational agents that I will talk about in the later part of the talk. We've been working on end-to-end trainable architectures for dialogue, social aspects of conversational AI, and natural language processing for classification of intents or tickets or other things, learning embeddings and visualizing embeddings for language, and the smart reply system. And of course, at Uber AI, we also do a lot of research on theoretical and more applied AI work, so I encourage you to look at our publications there. But going back to conversational AI, so we were doing all of this work, and we were wondering how can we put this in an agent. We tried to find an open platform where we can deploy or we can test all of these things, but we couldn't find something that was flexible enough and didn't need a lot of changes to support all of these different use cases. And so we developed Plato, basically with two principles in mind. One, that it has a very clean and understandable design in the dialogue so that newcomers, but also veterans, can easily understand what's going on and can extend it to their needs. And the other one was to be flexible to support all of these different kinds of architectures and use cases that we want to support. And so Plato is a primarily research and learning environment. It's also an environment for developing conversational agents and also for quick prototyping and demonstrating. It is not a product platform. It hasn't been designed to be a product, but it can be a common platform for research. So please take a look and see online for yourselves. I'll give you a brief overview of Plato. So Plato can talk to human agents, can talk to other Plato agents, and can talk to data in the sense that we load the data and train our statistical models. Zooming in a little bit further, Plato can get speech as input, text, or structured information in the sense of dialogue acts or intents, and can output speech, text, structured information, platform actions, statistical models, or simulated data. And zooming in even further, assume that we have a food ordering application. If someone says, I'm thinking burger tonight, then we get that from a speech recognizer. Plato doesn't have a speech recognizer in itself. But we can get, we then do language understanding, where basically we extract the meaning out of the sentence that the user said. This is forwarded to the state tracking model, where we keep track of the information that has been sent so far in the dialogue. We then do an API call. We see that there are no burgers. For some reason, we think that sushi is a nice option. So we forward that to our action selector or dialogue policy that selects the most appropriate meaning for the system to say, which is in the same space as the extracted meaning, the output of language understanding. This is fed into the language generator that generates a text that is fed back to the user. And now traditionally in dialogue, I guess maybe up to a few years ago, we didn't have a lot of dialogue data. And so people have been using simulated users to train their models. So if you have a model of a user simulator, then you can have your system interact with the simulator thousands of times until you learn good behaviors. And so Plato provides implementations for all of these components, but it also provides an easy way for you to put your own components there or other kinds of code or extract pre-trained models and put them there. Of course, this is the kind of standard architecture. Plato supports also jointly trained models or different kinds of things that I will show in a bit. So how can we use Plato to create a conversational AI application? We start with an idea. Then if you have data, you can somehow extract an ontology, which is the schema of the data. It describes the domain, train statistical models, and you have your conversational agent. But what if you have no data? Then you can come up with an ontology that kind of makes sense in the domain as an initial ontology. Use the simulator to create simulated data. You can use the simulated data to train weaker statistical models, and then have a conversational agent that can interact with people, collect more data, train better statistical models, and go into this loop. And so the simulators that we use, as an example, we have the agenda-based simulator, which is a very well-known simulator in the community. We also support more. The basic idea is we have this agenda of things that the simulator needs to say. It's implemented as a stack. And so what happens is we have our database of items, again in the food ordering domain. We can sample a goal, and let's say that the simulated user wants to order Italian pasta and request the price. So we then push into the agenda the dialog acts that reflect these, that would achieve this goal. And in the end, we push some, conversation kind of things like hello, goodbye, and anything else that's useful. So at runtime, what happens is the system says something, and the simulator in response may push some new acts in the top of the agenda, do some consistency checks, remove duplicates, and so on. And then to respond, it will just pop one or more items out of the agenda. That's generally how it works. Of course, we have other simulators, and you're welcome to put your own in there. Now, if you have data, Plato, you can write a parser. We provide some parsers, but you can write your own parser from the conversational data into what we call Plato conversation logs, which is the internal representation that Plato keeps for the dialogue, and then use Plato and the algorithms that are implemented in there to train all of your models. If you don't want to do that, you can also use something like Ludwig, which is an open source deep learning framework from Uber that requires very little to no code. So you can very easily prototype or train very strong models using CSV files that you can then import into Plato. And of course, you can use your favorite deep learning model framework, train your models, and put them into Plato. If you go the orange route, you need to write a little bit of code, but it's not something that is scary. Now, one other feature that Plato has is that it supports multiple agents. So we can run multiple conversational agents that can interact with each other. In the current version, we support 2, but it's very easy to extend the controller to support more, like, for example, a Blackboard architecture where each agent can broadcast messages to other agents. Agents can be trained online and can have different roles. For example, can be a system, a user, a tourist, and can have role-specific goals and role-specific rewards. So what is success for an agent of one role may not be the same as, what is success for an assistant may not be the same as for a tourist, for example. Another good feature of Plato is what we call generic Plato agents, and this is what allows the flexibility in supporting the different kinds of architectures. So the main idea is that all of the important, let's say, components that we have inherit from a class that's called conversational module. So all of the abstract classes that define the interfaces for NLU, state tracking, LG, policies, inherit from conversational module. And then your application-specific classes will inherit from those abstract classes. If you have a custom module that you want to implement, let's say a joint module from NLU to policy, then all you need to do is wrap your model around, inherit, I guess, from the conversational module and import it into Plato. To import it in Plato, you simply need to provide in the configuration file some of the class names and paths, so it's very easy. And the way that conversational modules talk to each other, if you have, let's say you can have 7 language understanding components, 1 DST, and then a single joint network that goes from state tracking to language, they interact via something that we call conversational frame that you don't need to worry about. It's done for you by Plato. But what it does conceptually is it wraps the information that is exchanged by the agents into this frame, and the information can be utterances, dialogue acts, speech, whatever you want. We have a lot of tutorials online, and we are, planning to release a new version that will be a little bit cleaner, a little bit easier. You'll be able to do pip install Plato and do a few other things, so stay tuned for that. So now I want to switch gears a little bit and talk about some of the research that we have done using Plato. We have trained 2 conversational agents by letting them talk to each other, and our domain is the very well-known Cambridge restaurants domain, where you have people who are calling the system. The system is providing information about restaurants in Cambridge, And people may be looking for an expensive restaurant that is vegetarian. They want to get the phone number, the address, and things like that. And so at the bottom, I have an example of what a database item looks like and the things that we care about, like addresses, areas, and things like that. This is the overview of our agent's architecture. So we have an information provider and an information seeker. And what happens is we have a language understanding model, dialog policy, and language generation for each of the agents that are similar in architecture but with different parameters. And so we want to train both of the agents by just talking to each other, and the vision is that we can augment the data, create more interesting conversations, maybe even have multiple agents, not just two. But this is turns out to be a very hard problem. And why is it hard? Because both agents learn simultaneously and they learn online. So it means that at the beginning, where they are still trying to explore, they are not behaving correctly, right? So it's very hard. There's a lot of uncertainty in a lot of the modules, and it's very hard, essentially, for an agent, let's say the dialog policy, to associate states with good actions, because other agents are exploring. Okay, sorry. So credit assignment is a very hard problem too. So if a dialog is failed, then how do we know what went wrong where? So for example, the provider agent wants to offer an item that matches the seeker's criteria and to respond to the seeker's requests. For example, what is the price, what is the phone number? The seeker wants to provide all of the criteria and make all of the requests. But if the dialog fails, for example, if the seeker never expresses a criterion or never makes the request, it's not fair to penalize the behavior of the provider, because the provider behaved very well, given the information it received. And on the contrary, of course, if a criterion is misunderstood or a request is unanswered, it's unfair to penalize the seeker. So as a first approach, this was a very hard problem. So we pre-trained NLU and NLG and trained our dialog policies with multi-agent reinforcement learning. And we chose win or lose fast policy hill climbing, where the general idea here is that we have two learning rates, one for when we are winning, one for when we are losing. Winning or losing means we keep track of, say, an estimate kind of average policy, and if we're doing better, then we're winning. If we're doing worse, we're losing. So we have a higher learning rate for when we're losing, so we learn fast from the mistakes, and we have a lower learning rate when we are winning. And so this seems to help and make the agents learn decently. So I'll briefly describe the LU and LG components. So for language understanding, we have a deep neural network. There we want to predict the intent and begin in-out slots, tags for slots and values. So what we do is we have the utterance, we pass it through an embedding layer, and then 4 convolutional layers with different filter sizes that produce some other, let's say, embeddings that we concatenate. And then we have 2 heads, one where we pull and pass it through a fully connected layer to predict the intent. So for request, we, instead of having intent and value, because sometimes the user can say, what is the phone number or something like that, that's not exactly a value, it's a slot. So then we found it better to kind of group these as intents, as in request phone, request area, and so on. And we have a tagger to produce the BIO tags. Now for generation, we used a simple sequence-to-sequence model with LSTM, where in the input we put as words what we want to generate, kind of a representation of the dialog act, so the intent and some of the slots. We can handle also a couple of acts there. And the output is a template, the lexicalized template, that we then fill with the item that we have received from the database. And now because this, the generator was trained on the data from DSTC2, the people that were calling the system sometimes would say price range or phone number, meaning what is the price range, what is the phone number. So the dialogues or the language is not very varied, it's very short. And so to kind of try to account for that, we found that if we had some context in the user's generator, meaning what the system said before, we can have a little bit better language. So to evaluate, we evaluate in 2 dimensions. So we have we evaluated our agents that were trained with multi-agent reinforcement learning against the supervised agents that were trained offline. And the other dimension was whether we would use dialogue acts as a communication, or we would use language understanding and language generation. And it seems that multi-agent approach performs much better. With the language, it doesn't perform as well in the number of turns, but we do maybe 1 turn more on average. So these are some dialogues that we generated. Okay, so I need to wrap up, I guess. So I will just talk about some current work that I guess areas of current work. Oops. Yeah, so we will continue to work on the training of the conversational agents, of course, training the LU and the LG at the same time. We're also looking into some joint architectures. We continue to work on end-to-end systems and social conversational AI, multimodal and multilingual agents. So, thank you.
Sorry to cut you short, but we have time for just 1 question. Alla una, alla due. 1 question. Okay. So maybe I could ask you just 1 little question. In your dialogue simulation, how do you do validation on the way people interact? Not people, I mean the turns back and forth.
In Plato, you mean?
In Plato, yeah. Do you have processes in place for that?
We are writing some scripts that can automate the process, yes. It's not currently in the repository, but we will do that, yeah. When we do experiments, we do that, we can run that a couple of times. So
to validate that.
Yeah, train, validate, and test, yeah.
Okay. Yeah. Excellent. All right, well, thank you very much again. And right now, I guess we're going to lunch.